this is the first lecture, well, actually lecture 0 in a series of lectures about mathematical epidemiology that was taught at NWU in South Africa in April 2022. And these are videos that I'm recording because during the event we were having a few issues getting the recording to work properly. Therefore, I decided to record these lectures again after having come back to Winnipeg, where I am now. So this first lecture, as I said, is essentially just to present the course content and make a few general remarks before we get started on the course proper. So before I go any further, I will point out that these slides are HTML files. I'll come back to that later, but I just wanted to point out that these icons and most of the links in these slides are clickable, and in particular, this is where you'll find my email. So, this being said, I'll start with a brief in memoriam. So this course is the first course that I'm teaching since the passing of Fred Brauer, who was a dear friend of mine and of many, many others. So Fred passed away last year, and prior to that we had taught in many summer schools together, and I learned a lot from him. So it's this course is in his memory because I think it's the sort of thing he liked to do. So I'll just point out, and there will be a few occasions for me during the course to point out like Fredisms. And here I will highlight one sentence that he loved to use from time to time when teaching, which is that one that I have at the bottom here. When you learn to use a hammer, everything looks like a nail, which I think is a very important sentence to remember when you're doing modeling. And there will be many occasions for me to point out where this type of problem comes up. So anyway, this is in memory of Fred. So the course itself, first, before I get into the details of what we will be doing, I first want to give some organizational issues. So as I pointed out, you have my emails on the first slide of every lecture. Don't hesitate to get in touch. I'll happily answer if I can. But I recommend using a subject tag such as something like 3NC in your subject line, because I get probably a bit too many emails, and it is likely that if you don't tag your email, I might miss it. The second thing that I want to highlight is that this course comes with a GitHub repository, and you will be able to access most of the content in this course by going to this repo, and I will show you where this is. So this is the HTML version, like the web version of the course. From there you have access to all the slides. I will add the links to the videos on the same page, but you also can access the project on GitHub. And if you do so, you'll end up on a page like this, which has the same info plus some additional notes here, as well as code, our code. I'll come back to that in a second. And a variety of content. Some of it don't pay attention to. This, for example, is part of the website version of the course. And if you're here and you want to go back to the website, you can just click here, which will take you back to the web part of the course. I should point out the slides, the original for the slides are also available here in this subdirectory, which you can generate then, as I will explain. Okay, so this being said, let me come back to the talk. So that's the repository. You'll find the slides, code, and data samples. I'll point out that I have not included any bibliographic references, downloaded papers here because of copyrights. But as much as possible, I have tried to use open source articles, open text articles, so that you can access them from everywhere. And the last thing I want to point out about this is that I also have used a lot of Wikipedia references. For the younger students here, I'll just point out that Wikipedia is a very good source of information, but you should use it wisely. It's a good place to start looking for information. It should not be your final destination. You can find info there. You can follow the links on the Wikipedia page towards more information, but do not consider Wikipedia to be the last place in which to gather information. So, then the slides that you're seeing right now, they're written in Markdown, which is a very simple text formatting language. The mathematical content is produced in LaTeX as part of the Markdown. And all of this is rendered to HTML using this code here, this program. And I've done most of my editing within Visual Studio Code, but you can edit wherever. Images are on the website that you're getting the slides from. So you will require internet access if you're reading the slides. And I have indicated as much as possible the provenance of figures so that it's clear where things are coming from if they are not figures that I made. I made a lot of the figures that are included here in the courses, but the ones I did not make, I am indicating where they come from. Videos, well, this is one, and I will be throughout the next few days recording videos for all the different lectures. I will post these videos on YouTube, where you will have access to them, and I will also edit these slides when all the videos are ready, with links to them as well in the slides. The code, you will see that I use quite a lot of code, and I will be using R, the stats programming language originally. I will point out that Python would be also a very good choice, but I tend to prefer R. There are instructions on the GitHub repo explaining how to set up R for the purpose of the course. And as I pointed out, there are code pieces, scripts, they're called. There are scripts that are available on the repo. And just for reference, there's a good little online book that's called R for Applied Epidemiology and Public Health that I recommend you take a look at. It is very much on the epi and public health side of things. It's not on the mathematical side of things, but it is a useful reference. Talking about references, these are some books mostly, except for this, which is a paper, the Herb Hefcott paper from 2000. The others are books. These are good references, I think, that illustrate different aspects of disease modeling in mathematical epidemiology. And I'll point out some abbreviations that you'll see again. So this is Fred Brauer that I was talking about before, but PVVB stands for Pauline van den Driesch, whose name will come up quite a few times in the different lectures. And C cubed is Carlos Castillo Chavez. So these are some references. There are many others, very good as well references, but these are my favorite right now. So now to come back to the course itself. So the sort of organizational part is over. Now let's look at objectives and overall plan of the course. So in terms of objectives, what I want to do is an introduction to Math Epi, and it's going to be very brief and partial. Okay, I want to make this clear. This is not a large Epi course. There's a little less than 20 hours worth of course material, whereas twice as much or even 3 or 4 times as much would be really required to get people to a good stage. But necessarily the course was held over a few days, and therefore I chose a few representative topics. So in terms of what I want to do is I want to introduce MathEpi through 2 main aspects: the problems that we are considering and the methods that we use to consider these problems. And we will be considering these with 4 main problems/methods in mind. So modeling techniques, mathematical analysis of models, computational analysis of models, and use of data. And I'm going to point out, and I will do so repeatedly throughout the course, that I think it's important to do these 4 things interactively. You should not be following this as a laundry list of things to do in a particular order. Of course, you will start with modeling, but you should go back to modeling if you get stuck somewhere, for instance. Okay, so the 4 topics, we're going to go over them in a second, but those 4 topics, you should really think of them as being linked and being followed in sort of repeatedly in any order. Now, modeling to start with. I'm going to stress throughout the course that this is a very important step that should not be neglected. So and that comes back to that favorite sentence of Fred Brauer's that I was talking about at the beginning. Is like, you probably know a hammer. That's going to be ordinary differential equations or partial differential equations, mostly. Don't restrict yourself to this. So think big, take the time. It is important to write a good model, and a good model might not use the technique that you're used to. So take the time and really do the modeling properly and try to understand what goes into models. And I will have a few places in the course where I will stress some of those aspects. You'll see that. Okay. At the same time, you should also try to remain simple. So think outside the box, try things, try new things perhaps, but also try to keep things simple. So that's going to be important. Now, the mathematical analysis then is typically what follows. You have written a model, you need to analyze it. And I will point out that about 20 years ago, or even more recently, this was to a large extent the sole purpose of a mathematical epidemiology paper. But there were, of course, papers that went further, but a lot of the literature did mathematical analysis of a rather simple model and tried to get as much detail in math as possible. And I think it's important to see this is still a very relevant endeavor, but it is one that you should carry out if your aim is really to look at the mathematics of the model. But if you're trying to make a difference in terms of public health or epidemiology and help understand the problem, you have to understand that these mathematical approaches, they don't represent everything. So if you're looking at a problem of global stability and you go to see a public health person and you say, well, I can prove that the solution is going to go to a disease-free equilibrium, so the disease is going to go extinct in infinite time. This is not very useful to a public health person, because infinite time can mean anything from not so long to a very long time, and perhaps 1,000 years. This is not valuable information. So if you're trying to make a contribution, you should really think in terms of, is it really necessary for me to spend a lot of time on this, or should I look at other aspects? And another aspect that I think is important is numerics. And I really always stress that numerics should come as a complement to the mathematical analysis. It shouldn't, you're not using numerics to show that the proof you made of some result is valid. Simulating the solution to a differential equation to show that solutions go to the disease-free equilibrium under certain conditions is not a valuable thing to do. But if you can show, for example, I was talking about the time that it takes for the solution to go to a disease-free equilibrium, if you can consider this from a numerical perspective, then you're helping understand the problem. Okay. So it's really important, in my view, to use the numerics to go much further. So your analysis will take you some part of the way, and where you cannot move anymore forward from the mathematical point of view, you complement with the numerics. Okay. And the last thing I'm going to say about numerics is I think it's very important to remember that making good figures is a good way to communicate information. And there is a tendency often in math papers to not spend a lot of time thinking about how to make a figure that conveys a lot of information. You should not have 10 figures to show something if you can find a way to aggregate this information and put it into one figure. And so I think it's a very good practice to spend some time thinking about how you're going to present information, and that information is typically going to be numerical information, and how you're going to present it in a way that is appealing and understandable. Okay, so that's part of the numerical work, and it can take several days to create a good figure. Spend the time. And finally, the last thing I want to talk about in terms of these different techniques is data. So our access to data has changed a lot. So even 20 years ago, it was much, much harder to gain access to some of the public health information that we need for modeling. Nowadays, there is a movement towards what is called open data that has made some of the data that we need much more accessible. And I want to advocate, and I will do so several times during the course as well, towards using data if it's available. Not necessarily making that like an absolute necessity to have data in your models, but to be aware of what data is available and to be aware of the context in which you operate. So I'll come back to that during the course as well. So finally, in terms of the organization of the course, this is the sort of overall layout that we'll be following. So there are, I believe, 12 different lectures. So some of them are lectures, the ones that show with an L in list, and some of them are practicums that are more like tutorials. Okay, and this is the overall plan of the course that we'll be following. And I want to point out again that this is a very partial view of what we will be doing. Of mathematical epidemiology. I mean, this is what we will be doing, but that is just a fraction of mathematical epidemiology. But it will give you a taste. And the last thing I'm going to do is show you this nice Guinea flag that I made absolutely by accident. I chose colors, and it turns out that when I was representing them, I ended up with this very this known flag, but it's completely accidental. This is simply to indicate, so when I have top level slides, so that will be the title slides for each of the lectures, they'll show up in red-ish colors, and that's so top part level information, and then sections will be shown in yellow, and subsections will be shown in green, and that will help you navigate the content. This is just the reason why I'm showing you this here.